a meditation on the paradox of a fire that does not burn with heat, but with silence. Across the universe lies a glow older than stars, older than galaxies, the cosmic microwave background, a relic flame stretched into coldness. It is not the fire of destruction, but the fossil fire of creation, cooled to near absolute zero, yet still burning as the faint afterglow of the Big Bang, invisible to the eye. It surrounds all things, shaping galaxies, dictating structure. Whispering of origins. This cold fire is the silent architect of the cosmos. It orders the vast web of matter. It reveals the age of the universe, and it may yet carry secrets about what came before time itself. It is a paradox, a fire that chills, a silence that speaks, a relic that still shapes the present. The mystery is not only how this cold fire came to be, but how it continues to sculpt the universe billions of years after its birth. The search for the origins of the universe did not begin with stars, nor with galaxies, but with questions whispered by the silence between them. For most of human history, the night sky seemed eternal and unchanging, a dome of stars scattered at random across infinite space. Philosophers and astronomers wondered, had it always been this way? Was the universe ageless, without beginning, without end? Or had it been born in fire, in a singular act of creation that left behind some trace, a scar, a fossil, a memory? The theorists and the prediction of a fossil glowing the mid-20th century, as physics began to uncover the laws of the atom and the stars, a bold idea took form. The universe, some scientists argued, had begun not in eternity, but in an instant of unimaginable density and heat, the Big Bang. George Gamow, a brilliant and playful Russian-American physicist, together with his collaborators Ralph Alpha and Robert Herman, carried this vision into the realm of prediction. If the cosmos had once been a furnace of pure plasma, then its expansion must have stretched and cooled that primordial fire. And if it cooled, then its glow should still exist, filling the sky not with visible light, but with radiation. Too faint for the human eye, they calculated that the universe today should be bathed in a background, glow just a few degrees above absolute zero, a fossil fire, a memory of creation itself. This was not metaphor, it was physics. If the Big Bang was real, the universe should still burn with its afterglow. But the prediction went largely unnoticed. For decades, it lay dormant, a line in papers few read, a whisper of cold fire hidden in theory. The rival vision, a steady state cosmos at the same time. Another school of thought imagined the universe differently. Led by Fred Hoyle, the steady-state theory held that the cosmos had no beginning, no end, and no need for a fiery birth. As galaxies receded, new matter was continuously created to fill the gaps, keeping the universe uniform and eternal. To the steady-state cosmologists, there was no cold fire to find. There was no relic glow, no fossil memory. The universe was infinite, timeless, and self-sustaining. Thus, the stage was set for one of the great confrontations in science between the vision of a fiery birth and the dream of eternal stability. And the deciding evidence would come not from theory, but from a most unexpected place: a telephone company's experimental antenna. The accidental discovery in 1965. Two engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were testing a large horn-shaped antenna designed for satellite communication. Their task was technical, not cosmic, to eliminate sources of noise that interfered with their measurements. But no matter what they did, a persistent hiss remained. It was not interference from the city, nor from the sun, nor even from the pigeon droppings they cleaned out of the antenna. The noise came from everywhere, uniform in every direction, day and night, season after season. Frustrated, they consulted with physicists at Princeton, who were, at that very moment, searching for the very thing Gamow had predicted decades earlier, the fossil glow of the Big Bang. When the two groups compared notes, realization dawned. The hiss was no accident. It was the sky itself. Penzias and Wilson had stumbled upon the cosmic microwave background, radiation from the birth of the universe, stretched by expansion into invisible microwaves in their static-filled antenna. Humanity had heard the echo of creation. The recognition of a relic flame, the implications were immediate and profound. The steady-state model could not explain a universal glow of ancient fire, but the Big Bang predicted it perfectly. The discovery transformed cosmology from speculation to certainty. The universe had a beginning. It had been born in heat and light, and that light still bathed the cosmos, cooled into near invisibility. Early measurements confirmed its properties. The radiation was uniform across the entire sky, smooth to within a fraction of a percent. It was everywhere, inescapable, eternal. The universe was not silent. It whispered constantly with the memory of its own birth, the paradox of uniformity and... Yet, within this triumph lay a paradox. The cold fire was smooth, too smooth. If the universe began with a hot, uniform plasma, then why did it not remain uniform? Why did matter gather into galaxies and stars? Somewhere in that smooth glow, there had to be tiny variations, subtle ripples in density that gravity could amplify into the cosmic web. But the instruments of the 1960s and 1970s could not detect them. The cold fire appeared flawless, and flawless meant paradox. A perfectly smooth universe could never give birth to complexity. Thus, the discovery carried both victory and mystery. The Big Bang was confirmed, but the seeds of galaxies remained invisible. The cosmos glowed with memory, but withheld its blueprint. The birth of precision cosmology, the search for those faint variations, became the driving mission of cosmology. Scientists knew they must exist. Without them, the universe as seen through. Telescopes could never have formed. In the decades to follow, humanity would launch satellites into orbit, free from the noise of Earth's atmosphere, to map the cold fire with exquisite precision. These missions would reveal the subtle ripples that seeded galaxies, unlocking the age, composition, and fate of the universe. But even in its earliest days, before those satellites, the discovery of the cosmic microwave background changed everything. It gave cosmology its first hard evidence, its first fossil. It proved that the universe itself carried memory, not myth, not metaphor, but measurable radiation filling every corner of space. The universe still glows today. That glow can be measured with a simple radio receiver. It hums faintly between channels on an old television set. A few % of static is not electrical interference but the afterglow of the Big Bang itself. Every household antenna once carried the proof that the universe still burns with a fire. 13.8 billion years old. It is not a fire of destruction, but a relic flame, cooled, stretched, silent, yet still present. The universe itself glows faintly, with the memory of its own birth, and in that glow lies a promise that the story of creation can be read. If only humanity learns to listen with enough patience, with enough precision, and with enough wonder. The discovery of the cosmic microwave background was a triumph, a sudden, accidental revelation that confirmed the fiery birth of the universe. Yet, as with every great scientific breakthrough, The glow of discovery carried with it shadows of doubt, paradox, and philosophical weight. The fall of eternity, steady state overthrown for years. Cosmology had been divided between two visions. On one side stood the Big Bang, proposing that the universe began in a moment of searing heat and density. On the other, the steady state, with its promise of eternal constancy. No beginning, no end, no creation story to unsettle human imagination. The detection of the cold fire ended the debate. An eternal universe could not explain why space itself glowed with relic radiation. The Big Bang, once controversial, became undeniable fact. Fred Hoyle, who coined the very phrase Big Bang as mockery, found his steady-state cosmos slipping away. His vision of a universe that always was and always would be gave way to a universe with history, with memory, and with mystery. For scientists, the cold fire was confirmation. For philosophers, it was a shock. The universe had a beginning, and beginnings demand explanation. The fire that burns. Cold, the very existence of the cosmic microwave background was unsettling. Here was a fire that did not consume, that did not blaze with visible light, but that hummed faintly across the sky in wavelengths, tuned not to the eye but to the cold precision of instruments. Its temperature was measured at just 2.7 Kelvin, a mere 2.7 degrees above absolute zero. Yet this was not a dead chill. It was the faded afterglow of the hottest fire that had ever existed, stretched across billions of years into near silence. This paradox, a fire that chills, a silence that speaks, captured the imagination. The universe itself was revealed, as stranger than myth, carrying within it contradictions that no human story had ever dared to tell. The uniformity problem, but within triumph lay tension. The first measurements showed that the cosmic microwave background was astonishingly uniform. Its temperature was the same across the entire sky to better than 1 part in 1,000. And therein lay the problem. A perfectly smooth universe could not give birth to galaxies. Without initial ripples in density, gravity would have nothing to amplify. The cosmos would remain an endless mist, no stars, no planets, no life. Yet here humanity stood, in a universe brimming with galaxies. Somewhere hidden within that smooth glow, there had to be tiny imperfections, fluctuations, mere whispers of variation that had seeded all structure. But the instruments of the 1960s and 1970s could not see them. To the technology of the time, the cold fire was flawless. The contradiction cut deep. If the cosmic background was as smooth as it appeared, then the very existence of galaxies was inexplicable. The triumph of discovery had birthed a new paradox, perhaps more unsettling than the mystery it resolved. The philosophical shock. A universe with memory beyond physics lay philosophy. The cold fire was not just radiation, it was memory. It was the universe itself, carrying the record of its own creation, written not in words or myths, but in photons that had traveled unbroken for nearly 14 billion years. For the first time in history, humanity could look not only outward in space, but backward in time. The light filling the sky was not starlight. It was older, more primal, a fossil flame from an epoch before stars existed. This shifted the human perspective. No longer was cosmology a speculative tale. It was a science rooted in measurement, in relics, in fossils, written into the very fabric of reality. The universe was not mute. It spoke, faintly, in microwaves. And what it said was haunting. I began in fire, and that fire still surrounds you. The challenge to intuition, the cold fire also challenged human intuition. Fire is supposed to be hot, destructive, consuming, yet this fire was cold, gentle, preserved. To say the universe was filled with fire, colder than ice, seemed absurd. But the absurdity was true. The discovery revealed how limited human senses are. 2 eyes tuned only to visible light. The sky seemed dark between the stars. But 2 instruments tuned to microwaves, it blazed with uniform brilliance. The universe was not dark. Human perception was blind. This realization carried a deeper shock. What other truths might lie hidden, invisible to the senses, waiting for instruments to reveal them? The beginning of precision cosmology, the discovery of the cosmic microwave background, marked the birth of precision cosmology. With it, the universe ceased to be mere speculation. It became measurable, quantifiable, testable. Already scientists began to imagine missions that could map this cold fire in detail to find the faint fluctuations that theory demanded. Those fluctuations would reveal the seeds of galaxies, the density of matter, the geometry of space, the age of the cosmos. The future of cosmology would be written in the faint variations of this fossil glow, the emotional weight of creations. But even as equations and missions took shape, the emotional shock lingered. The universe itself glowed with the light of its birth, a glow that filled every corner of space, every direction, every night sky. When Arno Penzias and Robert Wilson first measured the hiss in their antenna, they had no idea they were hearing the voice of creation. Yet in their noise lay the greatest discovery in cosmology. This realization reshaped not only science, but humanity's sense of place. To live in a universe filled with relic fire is to live surrounded by memory, to exist within a cosmos that never forgets. The cold fire, as paradoxically cosmic microwave background, was not just data. It was paradox made manifest. A fire that is cold, a silence that speaks, a perfection too perfect to explain imperfection. It confirmed the Big Bang, but raised new mysteries. It silenced one debate, but ignited another. It revealed the universe's beginning, but left open the question of how beginnings give rise to complexity. This was the true scientific shock. Not that the universe had a beginning, but that the beginning was stranger, subtler, more contradictory than anyone had dared to imagine. The cold fire had been found. The hiss in the Bell Lab's antenna had revealed the universe's oldest relic. But in its smoothness lay a haunting paradox. If the cosmic microwave background was flawless, then galaxies should never have formed. Somewhere, hidden in its glow, there had to be subtle variations, tiny seeds of imperfection that gravity could amplify into stars, clusters, and cosmic webs. To find them, humanity needed new eyes. COBE, the first glimpse of the blueprint in 1989. NASA launched the Cosmic Background Explorer COBE, a satellite designed to measure the cosmic microwave background with unprecedented precision. Unlike ground-based instruments, COBE orbited above Earth's atmosphere, free from interference, listening directly to the universe itself. Its results were profound. COBE confirmed that the background radiation was a perfect black body spectrum, the most perfect ever measured in nature. It matched the theoretical curve of a cooling universe with astonishing precision, silencing any remaining doubts about the Big Bang. But more importantly, COBE revealed the faint ripples, anisotropies in temperature at the level of 1 part in 100,000. These were the long-sought seeds of structure, the imprints of quantum fluctuations stretched by cosmic expansion into patterns across the sky. George Smoot, lead scientist of COBE, declared, "It's like seeing the face of God, not in a theological sense, but in the awe of beholding the blueprint of creation itself. For in those ripples lay the map of the universe's destiny." WMAP, sharpening the pattern of COBE, gave the first glimpse. The Wilkinson microwave and probe WMAP, launched in 2001, brought the picture into focus. Over 9 years, WMAP mapped the sky in exquisite detail, measuring temperature variations across the cold fire to millionths of a degree. The results were breathtaking. WMAP produced a full sky map of the early universe, showing hot and cold spots that corresponded to regions of slightly different density. These tiny variations, no bigger than a fraction of a percent, were the seeds of galaxies, the original architecture of the cosmos. From WMAP, scientists could calculate the precise age of the universe, 13.7 billion years. They could measure its composition, about 5% ordinary matter, 25% dark matter, and 70% dark energy. They could even confirm its geometry. The universe was flat, balanced between open expansion and eventual collapse. The cold fire had become more than an afterglow. It was a cosmic blueprint, revealing not only the past but the very laws that shaped the present. Planck, The Universe in Microkelvin, 2009. The European Space Agency launched the Planck satellite, humanity's most precise probe of the cosmic microwave background. Planck mapped the sky with resolution so fine it could detect temperature differences of a few millionths of a degree. Its maps were extraordinary, a mottled tapestry of blue and red, representing tiny fluctuations in the cold fire. Each spot was a clue, a density variation that would one day become a galaxy, a cluster, or a void. From Planck, the age of the universe was refined to 13.8 billion years. The proportions of dark energy, dark matter, and baryonic matter were pinned down with unprecedented accuracy. Even the rate of cosmic expansion, the Hubble constant, was extracted, though it would soon spark controversy with local measurements. Planck revealed that the cold fire was not just relic light. It was a cosmic Rosetta Stone. Encoded in its ripples were the answers to questions humanity had asked for centuries. How old is the universe? What is it made of? How did galaxies form? The seeds of galaxies, the discovery of these fluctuations, solved the paradox of smoothness. The universe had not been flawless after all. It had been seeded with imperfection, with quantum ripples frozen into place by inflation, ripples that gravity magnified into galaxies. It is a profound thought. Every star, every planet, every human being owes its existence to tiny fluctuations in the cold fire. Without them, the cosmos would be sterile, a mist of particles expanding forever without form. We are, in a sense, the children of imperfection, the heirs of ripples measured in millionths of a degree. The cold fire as cosmic blueprint. What COBE, WMAP, and Planck revealed was staggering. The cold fire was not simply background noise. It was the most important dataset in cosmology, a window into the earliest moment we could ever hope to see. Before galaxies, before stars, before even atoms, the cold fire carried the imprint of physics operating at energies no laboratory on Earth could reproduce. Its ripples were fingerprints of the universe at a trillionth of a second old. This realization transformed the cosmic microwave background into something more than relic light. It became a time machine, a record not only of the universe's beginning, but of the fundamental laws that shaped its unfolding. The emotional dimension there is an eerie beauty in this. The sky, once thought silent, is filled with a pattern older than the oldest star. Every photon of the cold fire has traveled unbroken since the universe was 380,000 years old, when atoms first formed and light was freed. To measure it is to touch the earliest chapter of creation. The maps from Kobe, WMAP, and Planck are not just data. They are portraits of the cosmos as an infant, still glowing with the fire of its birth. Humanity, billions of years later, has learned to read those portraits, to translate their faint variations into knowledge of age, structure, and fate. It is humbling to realize that the story of the universe was written not in words, but in temperature. Fluctuations a millionth of a degree wide, the blueprint and the unknown, yet even as the cold fire revealed answers, it raised new questions. The maps contained anomalies, strange asymmetries, unusual alignments, and the enigmatic cold spot that refused to fit neatly into theory. The cold fire had given humanity the universe's blueprint, but it had also whispered of mysteries yet unsolved. It was both revelation and riddle, clarity and contradiction. What began as static in an antenna had become the greatest map of creation ever drawn. But even this map hinted at a deeper story, one that lay beyond the reach of current instruments, perhaps even beyond the reach of the Big Bang itself. The cold fire had spoken with clarity. It confirmed the Big Bang, revealed the age of the universe, and traced the seeds of galaxies. Yet buried in its glow were whispers of something stranger, anomalies, irregularities, patterns that should not exist. These faint hints unsettled cosmology, for they suggested that the cold fire might carry not only the story of the Big Bang, but memories of something deeper, something beyond the beginning itself. The cold spot among the most haunting features. In the cosmic microwave background is a vast cold spot, first detected by WMAP and confirmed by Planck. Stretching across hundreds of millions of light years, this region is significantly cooler than its surroundings. In the standard picture, temperature fluctuations in the CMB should be random, small, and evenly distributed. But the cold spot is too large, too deep, too coherent. Some argue it could be explained by a vast void in the distribution of galaxies along our line of sight. A supervoid capable of slightly cooling the background photons as they traverse it. But even the largest voids seem insufficient to account fully for its size. This has led some to propose more radical explanations, that the cold spot may be a scar left by a collision with another universe, an imprint of something beyond our own cosmic horizon. If true, it would mean the cold fire carries evidence not only of our cosmos, but of others. The axis of evil another puzzle lies in the unexpected alignments of the CMB. When scientists analyzed the large-scale patterns, the lowest multipoles of the radiation, they found they were not random, as theory predicted, but oddly aligned along a single axis. This strange correlation was given a provocative name: the axis of evil. It should not exist. The cosmological principle insists the universe is isotropic, the same in every direction on large scales. Yet here was evidence of a preferred direction, as though the universe itself carried orientation. Some dismissed it as coincidence, an artifact of data analysis, but the pattern persisted across multiple missions. If the axis is real, it may point to new physics, perhaps a large-scale anisotropy in spacetime, or echoes from conditions before inflation smoothed the cosmos. Hemispheric asymmetry, still more anomalies emerged. when the sky was divided into two hemispheres, one half displayed slightly stronger fluctuations than the other. This hemispheric asymmetry should not exist in a universe governed by uniform initial conditions. Its persistence raised unsettling possibilities. Was the universe born lopsided? Did inflation fail to erase all traces of earlier structure? Or is there a deeper layer of physics that breaks the symmetry of the cosmos? The paradox of uniformity and complexity. The heart of these anomalies lies a philosophical tension. The cold fire is astonishingly uniform, yet filled with tiny ripples that gave rise to galaxies. It is both smooth and irregular, balanced and asymmetric. It confirms the laws of physics while whispering of cracks in their foundation. This paradox unsettles scientists. The CMB is supposed to be the cleanest signal in cosmology, the most pristine relic of the early universe, and yet, precisely because it is so precise, its irregularities carry enormous weight. Every anomaly, every asymmetry may be a clue to something deeper. The inflationary answer and its questions to resolve the paradoxes. Physicists proposed cosmic inflation, a brief explosive expansion in the first fraction of a second after the Big Bang. Inflation explains why the universe is so smooth overall, while quantum fluctuations stretched during that epoch explain the ripples that seeded galaxies. But inflation itself raises questions. What triggered it? What ended it? And why do anomalies remain if inflation smoothed everything? Some suggest inflation is eternal, still occurring in distant regions, spawning an infinite multiverse. In this view, the cold spot or the axis of evil could be signatures of collisions between our bubble universe and others. If so, the cold fire is not just memory of our beginning, but evidence of cosmic plurality. The whisper of pre-Big Bang physics others reach further still. Perhaps the anomalies are not scars of collisions, but echoes from before the Big Bang. Some quantum gravity theories, such as loop quantum cosmology, propose that our universe emerged from a prior collapse, a bounce rather than a beginning. If so, the cold fire might carry faint imprints of that earlier universe. In this picture, the CMB is not only the oldest light we can see, but a window onto something even older, a story erased but not entirely forgotten, the threat to cosmologies. Foundations for cosmology. These anomalies represent both promise and threat. If they are real, they point to new physics, phenomena beyond the standard model of cosmology, glimpses of realities deeper than inflation, deeper than the Big Bang itself. But if they remain unexplained, they risk undermining confidence. How can the blueprint of the universe contain features that theory cannot account for? How can the most precise map of creation also carry riddles that resist explanation? This is the escalation, the realization that the cold fire may not be as simple as once believed. It is not just an afterglow. It is a palimpsest, a layered record carrying traces of events, both known and unknown. The emotional unease for scientists. Anomalies inspire both excitement and dread. They are the seeds of revolution, but also the cracks in certainty. The cold spot, the axis of evil, the asymmetry, each could be noise, or each could be revelation. For philosophers, the unease runs deeper. If the cold fire carries evidence of other universes, or of time before the Big Bang, then the very concept of a beginning collapses. The cosmos becomes not a single story, but an endless library, and for humanity. The thought is humbling. We live in a universe that may bear scars of events that predate its own birth. We are not only inhabitants of this cosmos, but readers of its memory, deciphering patterns that may point beyond comprehension. The deepening mystery, the cold fire, had begun as proof, confirmation of the Big Bang. But as its details unfolded, it became more than evidence. It became a riddle. Smooth yet asymmetric, uniform yet scarred, it hinted that the universe is more complex than any model can yet capture. In its anomalies, the cold fire may carry the key to new physics, to deeper truths, to realities beyond our own. Or it may simply remind us that even the clearest signal is never free of noise, and that certainty in science is always provisional. Either way, the mystery had deepened. The universe glows with memory, but memory, like all things, is imperfect. And in those imperfections lie questions that could reshape cosmology itself. The cold fire revealed both clarity and contradiction. It confirmed the Big Bang, mapped the seeds of galaxies, and unveiled the age and composition of the cosmos. Yet, its anomalies, the cold spot, the axis of evil, the subtle asymmetries, demanded explanations beyond the familiar. To confront them, science ventured into speculation, stretching theory into realms where mathematics, imagination, and philosophy intertwine. Inflationary cosmology, the most widely accepted explanation, is inflation, the idea that in the first trillionth of a second, the universe expanded faster than light, smoothing out irregularities and flattening space. Inflation accounts elegantly for much: why the universe is so uniform, why its geometry is flat, why the cold fire appears nearly identical in every direction. The tiny quantum fluctuations present at that time were magnified into cosmic-scale ripples, visible today as the anisotropies in the microwave background. But inflation is not a complete answer. It raises its own questions. What drove it? What field or particle acted as its fuel? Why did it end? And why do anomalies remain if inflation erased all traces of earlier structure? Some versions of inflation predict that it never ends everywhere, that while it stopped in our region, it continues in others, creating an infinite multiverse. If true, then the cold spots might be evidence of a collision between our bubble universe and another, a bruise left by cosmic contact. The multiverse hypothesis, the multiverse, once dismissed as philosophy, has crept closer to physics through inflationary models. In this view, our universe is but one bubble in a vast cosmic foam. Most remain forever isolated, but occasionally bubbles collide. Such collisions could leave imprints in the cosmic microwave background, circular scars, alignments, or regions like the cold spot. Some researchers have searched for these signatures in the Planck data, though none are yet conclusive. The possibility lingers that the cold fire may be the first empirical evidence of a reality larger than our universe itself. Topological defects and cosmic strings. Another line of speculation points to topological defects, relics of symmetry breaking in the early universe, akin to cracks in ice as water freezes. Among these are cosmic strings, hypothetical filaments of immense density and tension stretching across the cosmos. If such strings exist, they could bend space and imprint distinctive patterns onto the microwave background, though no definitive evidence of strings has yet been found. Some anomalies in the cold fire resemble the scars such relics might leave. If confirmed, they would connect cosmology to high-energy physics, offering a glimpse into forces that operated at energies far beyond current experiments. Quantum gravity and loop cosmology still. Deeper speculations look not just to the moments after the Big Bang, but to the possibility of a before. Quantum gravity theories, attempts to unite general relativity and quantum mechanics sometimes predict that the Big Bang was not a singular beginning, but a bounce dot in loop quantum cosmology. For instance, the universe collapses under gravity to a minimum size, then rebounds into expansion. If this is true, then the cold fire might carry echoes of a previous universe, faint imprints of cycles older than time as we know it. These imprints could take the form of subtle correlations in the CMB, patterns unexplained by standard inflation. If such features are real, then the cold fire is not just a relic of our universe's birth, but a memory of universes before. The string theory landscapes through theory, with its vast landscape of possible vacuum states, also offers speculation. Each state could correspond to a different universe, with different physical laws. In this framework, our universe is just one valley in a cosmic terrain of possibilities. The anomalies in the CMB might be the fingerprints of transitions between such states, subtle scars from shifts in the underlying fabric of reality. If so, then the cold fire is more than fossil light. It is evidence of the universe's place within a greater multidimensional structure. The cold spot as a cosmic scaramon, all anomalies, the cold spot remains most provocative. If not explained by supervoids, it may be a scar of cosmic origin, a bruise from a bubble collision, or the shadow of a universe adjacent to our own. Though speculative, the idea carries profound weight. If the cold spot is real evidence of other universes, then the cosmic microwave background is not only the afterglow of our birth, but a window into the plurality of existence. Unknown physics whispers beyond the standard model there remains. Of course, the possibility that the anomalies arise from unknown physics. The standard model of cosmology, CDM, works with elegance and precision, yet it is incomplete. Dark matter remains unseen, dark energy unexplained. Perhaps the anomalies in the cold fire are hints of these mysteries, or of forces not yet imagined. They may whisper of new particles, new interactions, or dimensions hidden from ordinary perception. The cold fire may be the first crack in a wall that, once broken, will reveal a deeper structure of reality. The philosophical reach of speculation for philosophers, the speculations carry even greater weight. If inflation is true, then our universe is one bubble among countless others. If loop cosmology is true, then time has no beginning, only cycles. If cosmic strings exist, then the universe is stitched together with relic threads from creation. In each case, the cold fire is more than radiation. It is a message, a whisper from the fabric of reality itself, hinting that existence is stranger than imagination allows. The common thread, what unites all these theories, inflation, multiverse, cosmic strings, quantum bounces, is that they all see the cold fire not as an endpoint, but as a window. It is the oldest light we can measure, yet it may point to events and realities even older. The cosmic microwave background is not just a relic of the Big Bang. It may be a palimpsest, carrying layers of memory written across the fabric of space-time. Awaiting translation, the awe of the unknown for scientists. Speculation is not weakness, it is courage, the willingness to follow data beyond certainty, to imagine what lies on the other side of the unknown. The cold fire has carried humanity from debates over steady state versus Big Bang into the dizzying realm of multiverses, quantum bounces, and cosmic strings. It has transformed cosmology into philosophy, and philosophy into science, and it reminds us that every answer opens into new questions. The universe, revealed in microwaves, is both illuminated and obscured. Its fire is cold, its silence speaks. Its blueprint carries riddles. Theories rise, speculations grow, but the truth remains just beyond reach. And in that distance lies wonder. The cosmic microwave background revealed itself first as noise in an antenna, then as a perfect spectrum measured by satellites, and finally as a mottled blueprint of creation etched in millionths of a degree. Yet its deepest mysteries remain. Unresolved, the cold spot, the axis of evil, the whisper of asymmetry. To confront them, science must build sharper instruments, colder detectors, and more patient eyes. The quest is ongoing, for the cold fire still carries secrets, and only with relentless observation can they be drawn into light. Eyes on the polar sky. Some of the best instruments for studying the cosmic background are not in space, but on Earth, placed in the clearest skies available. At the South Pole, where the air is dry and stable, the South Pole telescope scans the faint microwave glow. In the thin air of the Atacama Desert in Chile, the Atacama Cosmology Telescope listens to the relic radiation with exquisite sensitivity. These instruments focus on the fine-scale structure of the cold fire, looking not just at temperature variations, but at polarization patterns, the orientation of the radiation's electric fields. Within these patterns may lie the faint swirls of B-mode polarization, evidence of primordial gravitational waves from the universe's earliest moments. If detected, these swirls would be the smoking gun of inflation, direct proof that space itself once expanded faster than light. But the signal is vanishingly faint, and the universe is filled with foreground noise, dust, gas, and the Milky Way's own emissions. The BICE PP2 controversy in 2014. Excitement surged when the BICE PP2 experiment, also at the South Pole, announced it had detected B-mode polarization consistent with primordial gravitational waves. For a moment, the discovery seemed epical, confirmation of inflation, a glimpse into physics at energies unreachable by any collider. But the joy faded. Further analysis revealed that the signal was not primordial after all, but contamination. From galactic dust, the cold fire had tricked humanity, reminding scientists that nature rarely yields her secrets easily. The lesson was sobering but vital. The search requires rigor, patience, and humility. The signal is there, perhaps, but it will take sharper instruments and deeper analysis to uncover it. Light Bayard and the quest for primordial waves to push beyond Earth's limitations. Japan's Light Bayard satellite, planned for launch in the 2030s, will map the polarization of the cosmic background across the entire sky. Its mission is simple but profound: to find the B-modes with clarity, or to prove they do not exist at detectable levels. If Light BRD succeeds, it will confirm that inflation once shaped the cosmos, turning quantum fluctuations into galaxies. If it fails, cosmology must rethink inflation itself. Either way, the cold fire will force new understanding. CMBs for a global effort. Meanwhile, on Earth, an international collaboration prepares CMBs for a network of telescopes across the South Pole and the Atacama, with thousands of detectors chilled to near absolute zero. It will measure the cold fire with unprecedented precision. CMBs will not only search for B-modes, but also refine our knowledge of neutrinos, the lightest and most elusive particles in the cosmos. Subtle signatures of neutrinos are encoded in the anisotropies of the microwave background. By measuring them, CMBs may reveal the sum of neutrino masses, connecting cosmology to particle physics in a way no collider can match. Neutrino backgrounds. The deeper fire beyond photons, there lies another relic, the cosmic neutrino background. These ghostly particles decoupled from matter even earlier than light, just 1 second after the Big Bang. They still permeate the universe, but at energies so faint they remain undetected. The cold fire carries their imprint indirectly through the way neutrinos altered the growth of early fluctuations. But one day, instruments may detect the neutrino background directly, revealing a fire even older than the microwave glow, a fossil from the first heartbeat of the cosmos. Probing the foregrounds to isolate the cold fire, scientists must also peel away the noise of the Milky Way. Galactic dust, synchrotron radiation, and cosmic foregrounds obscure the relic signal. Future missions combine multiple frequencies, disentangling the true background from local contamination. It is painstaking work, sifting the whispers of creation from the static of the present. But only by removing the foregrounds can the primordial truth emerge. The Hubble tension and the CMB, the cold fire, has also drawn scientists into another mystery, the Hubble tension. Measurements of the expansion rate of the universe from the CMB via Planck differ from measurements made of local galaxies and supernova. If this tension is real, it could signal new physics, perhaps dark energy evolving with time or interactions. In the dark sector, future missions may help resolve this discrepancy, revealing whether the expansion rate mismatch is systematic error or a true sign that them. The standard model of cosmology is incomplete. The long patience of science, these tools from South Pole telescopes to space observatories, represent humanity's attempt to listen more deeply to the silence of the universe. The search is painstaking, the signals faint, the risks of error high. Yet the rewards are profound. Every new map of the cold fire sharpens our vision of the universe's origin. Every new measurement tests inflation, dark energy, neutrino physics, and gravity itself. Each anomaly, whether illusion or revelation, pushes theory forward. Science is a dialogue with silence. The cold fire does not answer quickly. It requires patience measured in decades, collaboration across nations, and technology honed to impossibility. But the payoff is knowledge of the deepest kind. The story of creation written in microwaves, standing on the edges light by odd. CMBS for and other missions prepare to take flight. Humanity stands on the edge of revelation. Within the polarization patterns of the cold fire may lie confirmation of inflation, evidence of quantum gravity, or hints of physics beyond imagination. The relic fire that began as static in an antenna has become the most precise laboratory. In cosmology, it is not simply background noise, but the very voice of the universe's birth. The tools are ready, the tests are coming, and the cosmos waits. Whether the anomalies dissolve into dust or bloom into new physics, the cold fire will decide. The cosmic microwave background began as noise in an antenna, a hiss mistaken for interference, a whisper almost dismissed. Yet it became the greatest revelation in cosmology, proof that the universe was born in fire. That time itself has a memory, and that creation leaves behind a relic glow. It is both the faintest of signals and the most profound of truths. And as the science deepens, the cold fire transforms from mere data into philosophy, into reflection, into meaning. The fire that chills the paradox remains haunting. Fire 2. Human intuition is heat destruction, transformation, the blaze of energy-consuming matter. Yet the universe's oldest fire is cold. It has cooled over billions of years to just 2.7 Kelvin, barely above absolute zero. Still, it shapes everything. Without this fire, galaxies would not have formed, stars would not have ignited, life would not have arisen. It is not the fire of death, but the fire of possibility. It burns not with heat, but with memory. This inversion, a fire that chills, a silence that speaks, is a reminder that the cosmos is never bound by human expectation. Reality is not obliged to fit metaphor. Yet, in its paradox, the cold fire becomes poetry, a flame without heat that nonetheless shaped the destiny of all things. The universe as memory in the cosmic microwave background. The universe reveals itself as a being that remembers. Every photon of the CMB has traveled unbroken for 13.8 billion years, carrying information from the moment matter and light parted ways. To measure it is to touch the infancy of the cosmos, to hear its first breath echoing still. This is more than science. It is philosophy written in radiation. The universe is not mute. It speaks through fossils of light. It carries its own origin within it, allowing creatures born billions of years later to reconstruct the dawn of time. We are not separate from this memory. We are born within it. Every atom in every human being was once part of the same plasma that glowed in that fire. To look at the CMB is, in a sense, to look into our own beginning, the fragility of knowledge, and, yet, the cold fire humbles us. For even as it clarifies, it unsettles. It confirmed the Big Bang, but raised anomalies that theory cannot yet explain. It refined our measurements, but ignited tensions over cosmic expansion rates. It revealed seeds of structure, but hinted at scars that may predate the universe itself. It shows us that knowledge is provisional. Every answer is temporary, every model vulnerable. The universe hides deeper than any single observation can reach. Science is not final truth, but endless approximation. The cold fire reminds us that certainty is an illusion and mystery is eternal. Humanity's place in the cold fire, there is wonder, too, in the human role. A species on a small planet, orbiting a star in an ordinary galaxy, has built machines capable of hearing the relic fire of creation, from static in an antenna to maps. Drawn by satellites, humanity has transformed noise into narrative, hiss into history. The scale is humbling. To measure fluctuations in temperature a millionth of a degree wide, across a universe 93 billion light-years across, is to extend the human mind beyond its natural limits. It is to become more than biological, to participate in cosmic reflection itself. The cold fire connects us to the cosmos. It says, "You are part of this story. You are born not only of stars, but of the ripples that seeded galaxies, of imperfections frozen into the background radiation. Your existence is written in the cold fire's map." The question of origins, but perhaps the greatest weight, lies in the question it leaves unanswered. Does the cold fire mark the true beginning, or is it a veil hiding something deeper? Are the anomalies mere noise, or are they scars from before? The Big Bang? Is our universe singular, or one bubble among countless others? The cold fire does not answer. It only offers hints, faint patterns, whispers of possibilities. It tells us that the universe began in heat, but not why it began at all. It shows us the blueprint, but not the architect, and perhaps that is its final lesson, that the deepest questions are not meant to be closed, only approached. The mystery is not a failure of science, but the essence of existence. The cold fire as symbol in the end. The cold fire is more than relic radiation. It is a symbol, a reminder that the universe is alive with paradox, that silence glows, that emptiness burns, that beginnings echo across eternity. It is a reminder that we live in a cosmos that remembers, and that we are part of that memory. The cold fire is not outside us. It flows through us, as the atoms of our bodies were once part of the plasma that glowed with it. To measure it is to measure ourselves, our origin, our connection, our place in the great unfolding. Final meditation, the cold fire that shapes the cosmos, is at once fragile and eternal. It can be drowned in static, lost in dust, overlooked as noise. Yet it endures across billions of years, a relic flame that still orders galaxies, still encodes the laws of physics, still whispers of creation. To live in such a universe is to live in wonder, to know that even the emptiest silence carries. Memory is to know that nothing is ever truly lost. Perhaps that is the final gift of the cold fire, the assurance that the universe does not forget, that beginnings are never erased, that creation leaves behind light, however faint, however cold, still burning with the story of all that is. In its silence, the cosmos speaks. In its chill, it burns. And in its cold fire, we find both the memory of our past and the mystery of our future.